This chemistry demo is all about the amphoteric properties of metal hydroxides. We will examine these amphoteric properties by observing what occurs when we combine zinc hydroxide, which is a metal hydroxide, with a basic solution and an acidic solution. So there are a few terms to know for this demonstration. First is amphoteric. If a compound is amphoteric, it means it is able to behave as an acid or a base depending on what it is reacting with. The other term to note is metal hydroxide. Metal hydroxides are made up of a metal cation and a hydroxide anion. When doing this experiment, it is important to wear safety goggles and an apron, as we will be dealing with acids and bases that can burn or corrode your skin. If you get either of these substances on your hand, use soap and water to wash it off. To begin this experiment, we first need to obtain our metal hydroxide. To do this, we will combine sodium hydroxide and zinc nitrate. The balanced net ionic equation for this reaction is shown here. By looking at it, we can see that the reaction produces a precipitate, zinc hydroxide. In this reaction, the sodium ions and the nitrate ions are spectators, and they do not participate in the reaction. The solubility product constant, or KSP, of a compound is the product of the molar concentrations of the constituent ions, each raised to the power of its stoichiometric coefficient in the equilibrium equation. The KSP expression for the zinc nitrate and sodium hydroxide reaction is shown here. The KSP value is very helpful in telling if a compound is soluble or not. A smaller KSP value indicates that the compound is less soluble, while a larger KSP value indicates that the compound is more soluble. The KSP value for zinc hydroxide is 1.8 times 10 to the negative 14th, which is very small. This means that zinc hydroxide is not very soluble, which goes along with our conclusion that zinc hydroxide is our metal hydroxide precipitate. Here is the reaction. I'm adding about 60 milliliters of hydroxide to 50 milliliters of zinc nitrate, which produces this gelatinous white precipitate, zinc hydroxide. Since it's hard to see what the precipitate looks like through the beaker, this is what the precipitate looks like when the excess liquid has been decanted. Now that we have our metal hydroxide, we can explore its amphoteric properties. To do this, we must split our zinc hydroxide precipitate into two containers. To the first beaker, which now contains 1/2 of the zinc hydroxide precipitate, we will continue to add hydroxide. To the second beaker, which contains the other half of the zinc hydroxide precipitate, we will add hydrochloric acid. First, let's see what happens when we react zinc hydroxide with sodium hydroxide. For this reaction, we will add about 100 milliliters of sodium hydroxide to the zinc hydroxide precipitate. As you can see, this will cause the zinc hydroxide precipitate to dissolve. Zinc hydroxide is able to dissolve because when zinc hydroxide and sodium hydroxide react, they produce a whole new compound, a complex ion called zincate, which is soluble. You can see this here in the balanced net ionic equation. As you can see with this diagram of zincate, a complex ion is an ion containing a central metal cation bonded to one or more molecules or ions. This is where the amphoteric properties of zinc hydroxide come into play. When we look at the electron shell model of zinc, we see that there are 2 electrons in the 4th level. However, for a zinc 2 ion, the 4th level is empty. This allows for zinc hydroxide to act as a Lewis acid, or an electron acceptor. Since the other reactant in this reaction is sodium hydroxide, aka hydroxide, which has 3 lone pairs, it acts as the Lewis base and donates electrons to zinc hydroxide, forming covalent bonds. When 4 hydroxide molecules, which is the maximum number of hydroxide molecules that can fit around zinc 2 ion, you get zincate. We know that zincate is soluble because it has a Kf value of 4.6 times 10 to the 17th, which is very large. Kf is the equilibrium constant for the complex ion formation. The larger Kf value, the more stable the complex ion is, and the more soluble it is. With a more stable complex ion, it means that more of it is formed from the reaction, which means that the reactants, in this case zinc hydroxide precipitate, decrease. Therefore, the formation of the complex ion zincate due to the addition of excess hydroxide increases the solubility of zinc hydroxide. We will now see what happens when we react zinc hydroxide with hydrochloric acid. For this reaction, we will add about 75 milliliters of hydrochloric acid to the zinc hydroxide precipitate. As you can see, the zinc hydroxide precipitate will dissolve. Here's the net ionic equation for this reaction. As you saw in the video, zinc hydroxide readily dissolves in acid to dissociate and form zinc 2 ions and water. This is due to the fact that the hydroxide anion that comprises zinc hydroxide is the conjugate base of a weak acid. This means that hydroxide is very strong and really wants the H+ ion from the hydrochloric acid. Thus, it acts as a Bronsted base. At the same time, hydrochloric acid is a very strong acid, and it wants to donate its H+ ion. This is because chloride ion is very electronegative, and it draws the electron density towards itself, and thus weakens the bond between it and the H+ ion. This allows the H+ ion to be donated to the hydroxide ion in zinc hydroxide, forming water. This also causes the zinc 2 ion and the hydroxide to dissociate. The zinc 2 ion forms a salt with the chloride ions from the hydrochloric acid. The chloride ions are not shown in the net ionic equation, however, because it is a spectator ion. So that's all, but to recap, in this demo we saw how in basic solutions metal hydroxides act as Lewis acids, while in acidic solutions metal hydroxides act as Bronsted bases. So thanks for watching!